Welcome to another podcast. In this episode, we're going to be taking a look at the first of three cases dealing with constant coefficient linear differential equations, specifically second order equations. So we have a second order IVP here. In this case, this is constant coefficients. In a previous video, we discovered that if we have constant coefficients, there are one of three things that can happen. Either we end up with real distinct roots, we end up with complex roots, or we end up with repeated real roots of the characteristic equation. And so the first step here will always be to find the characteristic equation. It's a polynomial that depends on r. I've been using r as the variable, but it could be any variable. We turn the derivatives into algebraic powers, and this becomes r squared plus 4r plus 3. And we solve it equal to 0 for what are called the characteristic roots. So remember, this is the characteristic equation. And we're solving it for the characteristic roots. So we will factor. This factors nicely. And our characteristic roots are -3 and -1. Now, that will lead to a fundamental set of solutions. We've talked about that. One of the solutions is y1 equals e to the minus 3t. Remember, you place the root in the power of t. The second solution corresponds to the other root, and it's e to the negative t. And we've looked at in class and in the videos the fact that not only are these solutions, but they are also linearly independent. We've looked at the Wronskians of these. And so we know that this forms a fundamental set, which means that the general solution then of the IVP by the superposition principle is a linear combination of this fundamental set, which is C1 e to the -3t plus C2 e to the -t. Now we need to apply our initial conditions. So we'll start with y of 0 equal to 1. Y of 0 equal to 1 implies that, let's see here, we get C1 plus C2 equals 1. And y prime of 0 equal to 0 implies, well, if you look at y prime is minus 3C1 e to the -3t minus C2 e to the -t. And so if I evaluate it at 0, I have minus 3C1 minus C2 equals 0. And so we're back in Algebra 2 in high school. We're looking at the system of equations here. And so if we add the two equations together, we're going to eliminate the variable C2. So I'll go ahead and do that. If we add down, we get minus 2C1 equals 1. And so C1 is -1/2. And C2 is, looks like 3/2. So to find C2, I plugged C1 back into the first equation and then solved for C2. So putting it all together then, our particular solution, which solves the IVP, is y of t equals, let's see here, we've got our C1 is -1/2 e to the -3t plus our C2 is 3/2 e to the -t. And it's important that when you do this, you put the correct constant with the correct function, otherwise it's incorrect. So the -1/2 goes with e to the -3t, the 3/2 goes with e to the -t. So this is our particular solution, and we will talk about in future videos when we look at spring mass systems how this corresponds to what's called the overdamped case. So we'll take a look at those a little bit later, but for now you need to be comfortable with finding the characteristic equation, finding the characteristic roots, and then knowing the proper fundamental set from those roots, and being able to solve given initial conditions for the values of the constants C1 and C2. Remember, you're going to have two constants, but you also have two conditions. You have an initial position You have an initial position and an initial velocity, and those two are going to allow you to solve for the constants in the problem. All right, thank you for watching.